Alright guys, so welcome back from winter break and we're starting with number theory. So this lesson will be split into 2 days, so this is part 1. We're going to be doing examples 1 through 4 out of the 5.1 packet. So here we go. So from the time you were a small child, you've known about a set of numbers that's fascinated the great minds of history of mathematics for thousands of years. Let me find my highlighter here. The numbers that we use for counting, 1, 2, 3, and so on, are called natural numbers or counting numbers. Okay? This simple set of numbers has elegant properties and patterns that have intrigued mathematicians from ancient times to present. The study of natural numbers and their properties is called number theory. Okay? So that's the front side. All right. Now, the next side we're going to talk about prime numbers. One question that people have studied since time of the ancient Greeks is exactly which natural numbers can be written as a product of other natural numbers and which cannot. Okay? So we're going to underline this first sentence right here. Okay, for example, 30 can be broken down into 2 times 3 times 5 because those are all prime numbers. Now, and 17 can only be broken down into 17 times 1. Okay, so the fact that we cannot write 17 as a product of natural numbers without using 17 greatly interests mathematicians. In order to investigate this question, we have to explain what it means for one natural number to divide another. Okay, so I'm going to rewrite this whole thing. Okay, so if A divides into B, A is a divisor of B, and B is a multiple of A. Also, we can say A is a factor of B. Okay? So basically what I'm saying, if A goes into B, A is the divisor. Okay? And B is a multiple of A because it will go into it. Okay? So A is a factor because it goes into it evenly. Okay, so looking right here, 5 divides 30 because there is a natural number, namely 6, such that 30 equals 5 times 6. Also, we can write this more concisely as 5 and then this line 30. That lets you know that 5 goes into 30. Also, 17 goes into 17. Because 17 times 1 it gives us 17. When a natural number is a product of natural numbers, we say we factored the number. Hence why we call it factoring when we break something down in factoring. Okay? Some factorizations of 72 are 8 times 9. Or I can break this 8 down into 2 times 2 times 2 and 9 into 3 times 3. Numbers like 17, which have only trivial factorizations, are particularly important in number theory. Okay? So a natural number greater than 1 that has only itself in 1 as factors is called a prime number. So prime means only 1 in itself will go into it. If it has more numbers that go into it, it's called a composite because it's made up of lots of numbers. It's composed of more numbers. Okay? So prime means only 1 in itself. Now, it says numbers greater than 1. So what do we know about 1? Well, we say that 1 is neither prime nor composite. It just doesn't fit into any category. Okay, so numbers like 2, 5, 17, and 29 are prime numbers because only themselves and 1 are factors. On the other hand, numbers such as 4, 33, 87, 102 are composite because you can find divisors for them other than 1 and the number itself. One very well-known way to generate a list of primes is called the sieve of Erythocene, which is named after the Greek mathematician Erythocene of Alexandria. Okay, so this one's a little bit interesting, the way we do this. So, use the sieve to find all the prime numbers less than 50. So the first thing we're going to do is we're going to list all the numbers 1 to 50. So we're going to list them in rows of 10 right here till we get to 50. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then we're going to go 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, and 50. Okay, so how do we go about doing this? Alright, so the steps are the same every time. So step 1, cross off 1 because it isn't prime. Okay, so we're going to put a line through 1. Alright. Step 2, circle 2 because it is prime, but then cross out all multiples of 2. Okay, so 2 is prime, but then all the even numbers get crossed out after that because they're all divisible by 2. So we can just do each of the rows that end in 2, 4, 6, 8, and 0. Okay? Done with that step. Alright. Step 3. The next number in the list is 3. which is prime. Circle it. Then cross out all multiples of 3. So that's every third one after 3, okay? So 1, 2, 6, 1, 2, 9, 1, 2, 12, 1, 2, 15, 18, 21, 24, 27, 30, 33, 36, 39, 42, 45, 48, and that's it. Okay, next, let's go to our black pen for step 4. Next, circle 5 because it's prime. That's the next number available in our list. Then cross out multiples of 5, which are ones that end in 5 or 0. Okay, so we're going to circle 5. And anything that ends in a 5 or a 0, and all of those have been marked out. So we're slowly getting rid of the answers. Now let's go to our pencil here. Step 5. What's the next number available? 7. So we're going to circle 7 because it is prime. Then guess what? Cross out multiples of 7. So if you're trying to find out what the prime numbers are out of a list of numbers, as long as it's a small list, this isn't too bad. But if it said find all the prime numbers the 200, this would not be a fun time. So 7 times 1 is 7, 7 times 2 is 14, times 3 is 21, times 4 is 28, times 5 is 35, times 6 is 42, and times 7 is 49. So you do get to use your pencil one time. All right, now this next thing is kind of important, so I'm going to put a little star here. Number 6. Because the next prime (11) is greater than the square root of 50. So when you're doing these, it might benefit you to, like at the very beginning, say, okay, what is the square root of 50? Okay, so we go to our calculator. Square root of 50. And that's 707. So once you get to a number that's past 7, that's when you can do this. Okay? We can stop looking for composites and circle the remaining numbers in the list. So we can circle 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, and 47. So the list of prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, and 47. Okay? And that's how you do that. So, alrighty. So, it says in the next ones, determine whether the following numbers are prime or composite. So, the way that we're going to do this is we're going to check primes up to the square root of the number. Okay? So problem A, square root of 83 is 9.11. Okay? So does 2 go into this? No. Does 3 go into this? Because that's the next prime number. No. Does 5 go into this? No. 7? No. 9? No. So, none of these work. So we're going to go none go evenly into 83. So, prime. All right, let's do another. Square root of 87. This is 9.32. Okay, so we can check and say, does 87, does 2 go into it? And we knew that because 2 doesn't work. So we're going to check 2, 3, 5, 7, and 9. 87 divided by 3. Ooh, that works. So 3 goes into 87 evenly. So composite. All right. Let's do C. Square root of 397 is 19.92. So our prime numbers are 2, 3, 5, 7. Oh, 9 is not prime. 9 is not prime. Why am I checking 9? That's silly. You should have said, Miss Evans, what are you doing? 9 is not a prime number. Okay. And then here we have 11, 13, 17, and 19. Okay, so those are all the prime numbers. So we're just going to check to see if any of these go in. 397, we know 2 won't work. Let's try 3. Nope. 397 divided by 5. Nope. 397 divided by 7. Nope. 397 divided by 11. Nope. 397 divided by 13. Nope. 397 divided by 17. Nope. 397 divided by 19. Nope. Okay, so none go evenly into 397. So prime. Okay, so you just list the prime numbers up to the square root and try them and see if any of them go in. If any of them go in, the answer is composite. If none of them go in, then the answer is prime. Okay? All right. Now this next piece I'm going to need you to memorize because you're going to have a quiz on this. Divisibility test. So this will help you determine, and you know a lot of these already, to determine if a number is divisible by another number. So we're going to write right here. Memorize. Okay? So if the last number, and all I need you to do is memorize, like I'm going to write down these numbers, you're going to write down the rule. Okay? So you got to memorize these tests. So for 2, if the last digit is divisible by 2, in other words, if it's an even number, then yes, it will work. Now, 3, this is one that you probably didn't know. The sum of the digits is divisible by 3. So if I have all of these numbers, I add them up, and if 3 goes into that sum, then the number is divisible by 3. Okay? 4. If the last 2 digits are divisible by 4, then the number is divisible by 4. So if I have this big long number right here, 102,736, 36 is divisible by 4, so therefore that number is divisible by 4. We know the 5 rule, it has to end in 0 or 5 to be divisible. Okay? 6. If it's divisible by both 2 and 3, then it's going to be divisible by 6 as well. All right, 8. The last 3 digits, so the 2, 4, and 8 are kind of linked together. So the last digit divisible by 2, the last 2 digits divisible by 4. Here, the last 3 digits divisible by 8. So if the last 3 digits are divisible by 8, then the whole number is divisible by 8. And 3 and 9 share the same divisibility rule. The sum of the digits is divisible by 9. So you add up all the sum of the numbers, and if it's divisible by 9, then it works. Okay, 10, you know that rule already. So really you have 1, 2, 3, 4, 5 rules. That's it, because you know the 2 rule, you know the 5 rule, you know the 10 rule. Okay, and 3 and 9 are the same, so really you only need to learn 4 rules. Okay, so we're going to apply the divisibility rules. Okay, so here we're going to check this number for each of these rules. Okay, so the rule for 2 is last digit divisible by 2. Is that last number divisible by 2? Yep. So that works. Okay, let's go to the second one. Now for the sum of the digits, which is 1 plus 1 plus 3 plus 5 plus 2. Okay, so that's 2 and 3 is 5. 5 and 5 is 10. That's 12. 12 is divisible by 3. So that works. Okay? 4. Okay? Last 2 digits. Divisible by 4. 52 is divisible by 4. That's 13. So that works. Next, 5. Last digit is 5 or 0. That one does not work. Okay? And then E6 is divisible by both 2 and 3. So here, 2 and 3, yes it is, so that works. Okay, let's do F. Last 3 digits helps if you can spell. Digits divisible by 8. So 352. Good thing I have an eraser here. 352 is divisible by 8. Because 8 goes into 35 4 times with 3 left over. Bring that down, that's 32, so that's also 4. So 44. Okay, then let's go back and start with purple again. G, sum of digits 1 plus 1 plus 3 plus 5 plus 2 equals 12. 12 is not divisible by 9. So that's a no. Okay. And then the last one. Last digit is 0. That does not work. So this is a no, this is a no, and this is a no. This is a yes, a yes, a yes, a yes, and a yes. Okay? And that's how you do that. Really not difficult at all. Alright, one more thing for today. In chemistry, we form a compound by combining simpler objects called atoms. For example, a molecule of table salt is formed by combining 1 sodium and 1 chlorine atom. Similarly, in mathematics, objects are built from simpler objects. For example, 120 equals 2 times 2 times 2 times 3 times 5. And 84 is 2 times 2 times 3 times 7. Remember, this is the fundamental. Let's highlight all this. Similarly, in mathematics, objects are built from simpler objects. For example, 120 equals this, 84 equals this. Sorry, it's not straight. The fundamental theorem of arithmetic states that every natural number greater than 1 is built by multiplying a unique combination of prime numbers. Okay, all this simply means factor trees. Okay, and this was stated in its present form by the great German mathematician Karl Gauss. Okay, so all we're doing is making a factor tree. So we have 4, 6, 2, 0. Let's use a divisibility rule to get started. And let's use the biggest one we can. Okay, it ends in 0. So we can break this down into 10 times 462. Okay, now let's see here. That's 4 plus 6 is 10. That's 12. So we know 3 will go into it, but 9 won't. Okay, and it also ends in a 2, so 3 and 2 go into it. So that means 6 will go into it. So you could check on your calculator and see that 6 goes into that 77 times. We know that 10 can be broken down into 2 times 5. When you get to the point that the only thing you can break something down with is 1 in that number, you can stop. So we can stop here and here. Okay? 6 can be broken down into 2 times 3. Again, we can stop here and here. 77 is an easy multiplication fact. That's 7 and 11, both of which are prime numbers. So we can stop. Okay? So 4,620 can be broken down into, I like to go from smallest to largest, so I have 2 2s. I have a 3. I have a 5. I have a 7. And I have an 11. Now, sometimes you'll see it written a little more condensed. You see that you have 2 2s there, so you're going to see 2 squared times 3 times 5 times 7 times 11. And that's all for today. If you have any questions, please let me know.